Hello and welcome back to my YouTube channel. In this video, we'll be quickly learning about projection-based curve fitting. So let's take a recap. First, we discussed about the definition of the L2 norm. Then we discussed how to do interpolation kind of fits. Then the creation of von der Monde matrix. And then we faced some issues with the fitting of the Gaussian function and the Heaviside function. So now first, let's take a look at the Heaviside function and the Gaussian function in detail. So let's look at the Heaviside function. We first plot the Heaviside function and then fit an interpolating polynomial of order 10. Now the L2 error is 3.23 e to the power minus 1. So it's a substantial error. But now if we do a projection based fit, the error is lowered to 2.46 e to the power minus 1, which is not substantial, but still it's an improvement, particularly at the boundaries. So now let's plot the error profile of the projection based fit. Now you'll see that the errors at the boundaries are significantly lower than the interpolation based fits. So why does this happen? And at the center, the error profile remains almost the same. Let's take one more example of the Gaussian function. Now here you'll see that at the boundaries, the error in the interpolation fit is significant. So now the red curve is the interpolation fit and the error in the normed value is 2.32. But if I do a projection based fit, then the error is lowered by one order and then the error becomes 2.27 e to the power minus 1. Again, plotting the error profile, we'll see that the error distribution is not uniform in interpolation kind of fits. But while when we are doing a projection based of fits, we are having a very uniform distribution of error throughout the domain. So why does this projection method works better than the interpolation fit? So let's find out. Let's start with a very basic definition of projection of a 2D vector along the axis. So let's say if I have a vector 2, 1, then projection of it along the x-axis becomes 2i hat, while the projection of it along the y-axis becomes 1j hat. Now, if we have the error vector v minus projection of v along x, we see that it is perpendicular to the x-axis. Similarly, the projection of v along the y-axis is perpendicular to the j hat. So why does this orthogonality of error matters? So let's take a deeper look at the error vector. So now we take the same example, but we look at it through the definition of an orthogonality of error. So what we'll basically do, we'll have different choices of x such that we have a vector along the x-axis which we assume it to be the projection of v. And then we calculate the length of the error vector. So for the first choice, x is equals to 1. Now the error value becomes 2 minus 1 square plus 1 square. For the second example, we take x equals to 1.5. Similarly, for the third example, we take some value beyond 2, let's say 2.1. But still, the error vector is large. But for x equals to 2, error vector is the minimum. So we can say this orthogonality in a sense minimizes the distance between the vector and its projection on certain axis. Now we take a look of calculation of projection vector using the inner product or the dot product of two vectors. So we take two vectors u and v, which has an angle theta between them. So now I want to calculate the projection of u along v. So now I'll create a rectangle such that u is its diagonal. So now the two vectors a and b, a lies along v while b is perpendicular to v. So now the composition of a plus b is u. Now we can say that this a vector was essentially the projection. But how do we calculate it? We take the dot product of u and v divided by the dot product of v with v and then multiplied by the v vector. Similarly, if now u was perpendicular to v, now the dot product is 0. So now u doesn't have any projection along v. Similarly, if u was minus v, then the projection becomes minus 1. So this as a definition can be extended to functions. So how do we do this? We define the inner product in sense of integrals instead of summation, and we describe functions instead of discrete vector components. So now this is the formal definition of an inner product of two functions. And consequently, we define the definition of projection of one function to another function or a function space. Now, how do we use this? We form a minimization problem to be used as curve fitting. So we take the formal definition of L2 norm and then square it divided by 2 to form a potential. Now potential J is half of E squared dx, where E is f minus f bar. F bar is our approximation and f is the exact function. F bar can be alpha I x to the power I, which we are using till now, or it can be some general basis function, phi I. Now we take the derivative of J with respect to alpha j's and set it to 0 to form the minimization problem. So extending the definition, del j by del alpha j is integral of E times del E by del alpha j dx equals to 0. We expand on E. So now this becomes f minus f bar times del f bar by del alpha j dx equals to 0. Putting all these values in the discrete form, f bar is alpha I x to the power I. For simplicity, we can replace x to the power I with any phi I. We form this system of ku equals to f, where kij will be an integral discrete value of xi times xj dx, while fj will be f times x to the power j dx. And now we solve for u. This u is the solution of a least squares projection system. So this is the best possible approximation in sense of L2 norm. All this is useless if we cannot have a working code to implement all these things. So let's now focus on the algorithm for projection based fitting. So we take the f bar. For a quadratic fit, it will have three coefficients, alpha 1, alpha 2 and alpha 3, multiplied by 1, x and x square respectively. So this means phi 1 is 1, phi 2 is x and phi 3 is x squared. So now we form the f vector, which will be phi I times the exact function integrated over the domain, while kij will be phi I times phi j integrated over the domain. For this particular example, since we know all the phi I and phi j, k will be a 3 by 3 matrix corresponding to these values. And now we just do the inversion to find the coefficients alpha. So now let's go back to our Heaviside example and see the basic differences between an interpolation fit and a projection based fit in a little more detail. So now we have a 10th order polynomial with the interpolation being the red curve. The boundary errors are very large, but with projection based fitting, the boundary errors are small, and we can see that the error in the non-values in the projection based fit is lower. But if we look in detail the error profile, the major contributor to the error is the part in the middle. So if somehow we can take care of that part separately by some function which is very similar to Heaviside function, the rest of it will be almost 0. So what we do, we take the Heaviside function as before, and now we divide the domain into 3 parts. First will be from minus 2 to minus epsilon, then minus epsilon to epsilon, and then epsilon to 2. And we just do a linear fit. We just use 3 linear basis functions in 3 different parts. And then if we plot the error profile, then we'll see the error is 0 in the first domain, non-zero in the second, and 0 again in the third domain. We can figure out by some minor calculations the fitting functions, and then we can also include those functions to calculate the error values. So the contributor in the first domain will be 0. In the second domain, the error contribution will be epsilon by 6, and the third again 0. So this gives the basic idea of creating finite elements so that we can keep the errors locally. So here we can clearly see that the error is now a function of epsilon, and if we create a very small epsilon, then the error itself will be very small. So now these are the questions that we'll be going to answer in the next video. First will be how to do these piecewise polynomial fits. Then second will be how to create piecewise basis functions. And third, the most important part, how this is linked to the finite elements method, because this is our goal from the start, to understand finite elements method. So stay tuned to find the answers and download the codes from the description and start experimenting on your own. Take different functions and get your hands dirty. Please like, share and subscribe this video. That keeps me motivated to create more such content. Thank you for your time.